Okay, we're starting the next talk. So we have Vishal from IIT Bombay, who's going to talk to us about basics of clouds and convection. So Vishal, take it away.
Yeah, thanks, Jim. Hi, everybody. I'm Vishal Dikshit. So until now, we have heard quite a lot about how flows occur on different time scales and spatial scales. This talk is going to be a bit different, and it is going to be about clouds and convection. That does not mean it is not going to be about flows. So it is about how flows interact with other thermodynamic properties of atmospheric boundary layer. So, but to just motivate this, why to study clouds and why not just to continue with the nice Navier-Stokes we have already, and there's a great progress that we have made, and there are some open questions. Why to look at clouds and convection at all? And maybe why not just to kind of continue with the fluid dynamics that we already have some handle on. So just to motivate that, maybe I'll take some time to tell you that how clouds are a bit different than just the fluid dynamics that they are embedded in. So let me take you to very long time scales. Is everybody able to hear me? Yeah, I don't get good feedback. Yeah. So that means so on x-axis right now, time goes towards left, and the age is in years before 1950 CE. And it's, you can realize this is thousands of years. On y-axis, there is global temperature difference in delta centigrade. And you can notice that Earth was around 7 degrees colder around 20,000 years ago when the last glacial interglacial cycle ended, and Earth became around 7 degrees warmer. That's where we were at 1950 CE. And in past 100 years, we have already crossed 1 degree, or we are about to cross 1 degree, depending upon how you measure it. But the point is, our civilization, depending upon where you are, I mean, you will start probably to the left of a particular point, but our civilization thrived on this. And that means we are leaving this regime in which we are sitting in. My idea is not to actually scare you, but to tell you why clouds, water vapor, and convection are interesting and why we should care about them. That's step one in realizing that our climate is habitable because we had a nice temperature regime. Oh yeah, this should work, right? Yeah. Okay, now let's look at a history of CO2 in the atmosphere. I'm sure you have heard this, seen this plot in several other talks. So I will not take a lot of your time unless, so quickly tell me, so again, x-axis is thousands of years ago, CO2 concentration. We are here right now. So we are definitely doing something different than what, I mean, whoever used to live before was doing. And we are doing it significantly differently. It was around 408 ppm. What is it now? 420 is the right answer, yeah. So around 420. Although, again, we don't understand atmospheric turbulence enough, so we don't know how well carbon dioxide is mixed. This observation is from one point in the ocean, which is supposed to represent, which is a good representative of what it is. So it's around 420 today. Okay, my third slide is also about past climate. And now we are looking at methane composition in the top, carbon dioxide, and temperature change. And you will notice that carbon dioxide and methane have gone up and down. And along with that, temperature. So carbon dioxide and temperature are strongly coupled. And quickly tell me which words better describe the variation in CO2? Linear? Yeah, somebody quickly. Non-linear. Probably cyclic. Yeah, I'll take non-linear and cyclic, although this time series is not sufficient to give you enough of what it is. by and large, we would say it's size. Sorry?
It seems like that.
It seems like a random change. There's some pattern right there. So, yeah. Is it not? It's kind of doing some oscillations, right? And then we would want a longer time series to analyze. Okay. What has our Earth been through over the time scale of billions of years? A pale orange dot. Then 630 million years ago, whole Earth was covered with ice. And then dinosaur era, 230 million to minus 66, whatever, 66 million years ago. Then the last ice age, what we just said, were 20,000 years ago, and the present day, right? And then the composition of Earth also has changed. And very soon you will realize that what Earth's atmosphere is made up of really kind of is tied to what sort of equilibrium our Earth sits in. So I'm hoping that you will hear about more on this from later on from Anshuman, probably also from Ashwin, when they talk about what sort of decides the equilibrium of Earth's climate. Okay, so now let me kind of ask you what makes Earth's temperature habitable. We saw its temperature, right, where our kind of civilization thrived. The answer is partially on the slide that it has to do with something with these four people, I mean, and several others. I have just picked these four. So Fourier is a famous Fourier. He was kind of looking at absorption properties of gases, and he noticed that both water vapor and carbon dioxide actually have a greenhouse effect. They interact with the radiation in the long wave spectrum, and that means they have ability to interact with Earth's radiation budget. Then Tyndall, who was interested in actually finding out how do glaciers migrate, he was interested in that problem, and he found big icebergs where they should not have been found. And then he was wondering, why kisne laya ye iceberg yahan pe? And one of his theory was, over thousands of years, climate has changed, and that iceberg has come from somewhere else because temperature has been going up and down. And in the process, he was a great chemist. He did experiments and found out that what he actually kind of found out the bands in which water vapor, carbon dioxide absorbs. And Arrhenius did the first proper calculation of how much temperature change should we expect if greenhouse were to be accounted for. But his calculation were based on still very simple calculations as compared to what we can do now. This Callendar was a very interesting person. He was an engineer who was interested. He was from United Kingdom, and at that time, little ice age was going on, and they were kind of already kind of pissed with the cold temperatures that they were seeing. So he said, "Oh, probably this warming is good. At least we'll see some good days." But this guy did a lot of meticulous calculation about how much warming should you see. Now you will realize I said that I'll tell you about clouds and convection. I also made some connection to the turbulence that previous speakers were kind of telling about. And then I directly changed my kind of gear and started telling you about thousands of years ago how climate has been changing. The common part is these greenhouse gases. The gases, carbon dioxide, methane, water vapor. Now we understand pretty well how they kind of cause warming. So let me now kind of start telling you a bit about the vertical structure of atmosphere with this background of that the gases matter. And I ultimately want to convince you that water vapor matters most. That's my whole point in telling you this story. Remember, water vapor matters a lot for Earth's climate. So that's how kind of pressure decreases, density decreases with height. And then you will realize that 90% of atmospheric air mass is in the troposphere. This is the last 15 kilometers in tropics, 10 kilometers away from the tropics. These are like ballpark numbers. And amongst this last 10 kilometers or 15 kilometers, water vapor lies in first couple of, 90% of water vapor lies in first kilometer or a couple of kilometers. And all that happens, all the weather phenomena that we see ultimately is driven in these last 10 kilometers and mainly from how water vapor is transported upwards and what it does when it is transported upward. So essentially, all that we want to understand is how this interacts with the rest of it and also how this interacts with the oceans. But I think previous speakers have made some points about those. So that's today's picture actually. We saw sudden change in rainfall just a couple of days ago. And if you were noticing before, you will notice that this picture shows upper level water vapor. This is from INSAT. And more the white, the more abundance of water vapor in the atmosphere. You will notice that there are these black patches which nicely sit around monsoon region. And that means a lot of water vapor is, our atmosphere is right now populated with a lot of water vapor with very tall clouds. But with that, let us kind of revisit the fundamental properties of water vapor. There are several others, but I would like to highlight three very important properties. One is that the latent heat of phase change of water vapor is significantly more. Sometimes 6-7 times more than many other gases. What does that mean? For the same amount of condensate, you will have much more amount of energy that is released. Yeah. So if you were to carry water vapor with you, and one way or the other, you can kind of make it kind of undergo phase change, you can carry a lot of energy basically along with you. That's how you should think of it. That atmosphere has a lot of energy near its surface. When it is transported upwards, you are making that energy available for driving circulations and so on. Yeah. The other property of water vapor, which is very different from many other gases, is its ability to interact with wide range of radiation spectrum. And here, I would like to draw your attention to the structure of water molecules. So that's oxygen atom, right? With a lone pair and hydrogen, right? And it's not symmetric. So this simple, it's not simple structure, this simple looking structure gives water a lot of freedom. And then that means water can interact with vibrational energy, rotational energy. So basically it's not symmetric, as you will notice. So because it is not symmetric, several other possibilities arise. And then it can interact with photons. And in different radiation bands, it can basically control how much energy is either available on the surface or near the top of the atmosphere or at different altitudes in the atmosphere. We will look at that a bit, maybe a slide or so. The third property is that molecular weight of water vapor is 18 and average weight of dry air is more than 18 or less than 18. More, the answer is here. How much is it? 28. Yeah, around 29. You can say it's mainly nitrogen and oxygen. So it has to be between 28 and 32, right? Somewhere in between that, depending upon the mass ratio. So it is significantly lighter. Significantly lighter than the dry air. So that means if you were to just leave water in the vapor form as it is, it would want to go up. Just that because of surface tension and so on, water is in the liquid form, so it's not easily available for atmosphere. If that were to be so, it will keep on going up. And at some point, you might have runaway situation. I don't know if you have heard of this runaway greenhouse gas situation. We don't want to, I don't want to scare you, but want to tell you that this is a very important property of water vapor that you should remember. And these all play very important role in radiation and convection. Okay. So I told you, so to put things in terms of equation, we should think of vertical structure of atmosphere, where humidity is mainly in the boundary layer and decreases exponentially with height. Temperature decreases as the lapse rate of around 6.5 Kelvin. So by the tropopause, that's where the most of the interesting stuff happens. And what decides if a particular water molecule will remain in atmosphere or not is this Clausius-Clapeyron relation, which relates the saturation vapor pressure with temperature. And the point is this beta for water vapor, which is enthalpy L by R, for water vapor is 3 to 4 times more. And that means for unit change in temperature, you have much more change in the partial pressure of water vapor. And by Dalton's law of partial pressure, you will realize that that means it's more and more difficult to saturate. Right? You'll have to add more and more molecules, after which it will saturate. Okay, so let's move on. So I think I briefly mentioned, I don't want to spend a lot of time on this, but look at the number of vibrational and rotation. Vibrational and rotational bands water vapor has, and that is because water molecule does not exist just like this, but also forms crystals depending upon what altitude you are at. And these crystals, depending upon their geometry, also have their own radiation properties. So remember, water vapor is associated with, tightly coupled with radiation. It's one of the most potent greenhouse gases. Our today's lecture is not about radiation, so I'll stop talking about radiation, but that's the role water vapor plays in the mix. Sorry? This one? These are relative lines of intensity. So if you look at the radiation spectrum, who asked the question? Yeah. So these are relative intensity. Yeah. Okay, now I think that's the last slide about why we should study water vapor. And here on x-axis, we are looking at surface temperature change in response to doubling of carbon dioxide, something that many climate scientists like doing. Although it's a bit hypothetical, it is a good ballpark number. What is the response of climate system to doubling of CO2? If water vapor was not there in response to doubling of carbon dioxide, purely because of radiative effects, we would have got something around a Kelvin warming. If water vapor was there, but clouds were not to form, that means water vapor had radiative effect, it had its lesser molecular weight, but clouds do not form. That means condensation process is somehow muted. So it's like a passive but radiatively active gas. Then you would reach something like maybe 2.5 with some kind of uncertainty bar on top. But because you have clouds, look at what is the range of uncertainty we are sitting in. So that means from policy point of view, what policy should you design based on this? Oh, it can be either 2 or it can be 4.5. Does it help? No. So in some sense, if you really want to understand how dynamics on the rotating planet affects climate, you should understand how water vapor interacts with the dynamics. That's the kind of point, how clouds form. Okay, now let's go to a plot. I have not seen this plot being shown, which probably you showed. No, yeah, this is a usual plot that everybody shows, irrespective of what you work on. And on x-axis, there is space scale, which goes from micro scale, meso scale, synoptic scale, planetary scale, and so on. And y-axis is time. And you can see that the previous speakers, as well as a bit of what I'll show, lies here. That's where we sit. 1 second, 1 meter. That's our length scale, time scale. So we use DNS turbulence models or large eddy simulations, something that previous speakers were telling. Weather sits here, hundreds of seconds. If you watch cricket match in England, they predict in 10 minutes there is a shower. After 15 minutes, it goes away, right? Okay, so then there are cloud resolving or mesoscale models. the tornadoes, water sprouts. I don't know if you have seen these nice animations, but they all sit here. There are climate models, or maybe there are future global models which will want to resolve something like a kilometer, but resolve variability on the scales of 50 kilometer and so on very, very well. So the point is the cloud microphysics, that means the water vapor which is sitting along with the cloud condensation nuclei and wanting to make clouds matters here. So here cloud microphysics matters. On these mesoscales to synoptic scales, convection circulation interactions matter. And by convection, I do not just mean precipitating convection, right? Convection is anything that is driven by buoyancy, something which is lighter than something else, which drives circulations. Yeah? So all those effects will matter here. But as the time scale becomes longer and longer, it becomes radiation convection circulation problem. Can somebody tell me why is radiation not in this? Time scale, yes. The time scale of radiation is small, although it's all pervasive, the time scale is small. So it takes a bit of time for it to matter. Although it is occurring at photon scale, right? It's every photon is doing radiation. It's basically electromagnetic radiation. But for it to matter significantly, you have to reach a particular length and time scale. And then we started our talk with by showing you radiation, right? What is the chemical properties of gases that really shape our climate. Okay, so these all different scales matter. Now let's look at this very nice animation from Stu Ostro's Twitter handle. You can see a nice cloud cluster developing on the time scale of few hours. So can somebody tell me why is the base pretty flat? And can you count how many nice thermals, I don't know if you have heard of this word, these nice blobs of cloud which are wanting to grow, can we count them? Maybe not, right? I mean, they are a bit like fractal. They are developing on very fast time scale. And in some sense, what I'm asking you to do is tell me, can you really simulate that, right? That's the question we are talking about. So this is on the order of few hours, maybe something like a couple of hours to around half a day or so. And these are mainly vertical, but there's some amount of water vapor and condensate also going away from it. But it's by and large vertical. Okay, now let's look at some nice animations. How much time is? It's like 15 minutes?
Yeah, we haven't taken.
Oops, it's just 15 minutes more? Okay, yeah. Okay, so I'll quickly show you animations, but I have to, so this particular thing is what satellites see, and what we see is here. This is all over the place, right? Whereas there is a particular coherent structure here. So that means the background vorticity is anchoring clouds and convection in this. Whereas, do you see any structure here? Maybe there is vorticity. There is, of course, vorticity since it's developing and so on, right? But there is no coherent structure here. It's all over the place. So the point being, there are sometimes vorticity modulates convection. At other times, things go all over the place. Maybe the scales are different. This is kind of planetary scale, if you like. This is mesoscale, synoptic scale, much 100-kilometer scale, thousands of kilometer scale. Okay. The same animation that Jim showed, I would like to show. Now notice how different are systems, clouds, when they form near equator or when they form away from the equator. So you'll notice that, oops, let me play it again. Here they are being anchored along with, so they like to ride along with the waves that people have been talking about, right? Rossby waves. Or flows which are driven by quasi-geostrophy or baroclinic instability. I don't think you discussed about it, but mid-latitude you did. So there's something called baroclinic instability that drives these. Whereas near the equator, you'll see that's not so, right? It's by and large like popcorn convection. So convection is not known to sit on any particular wave. Although if you zoom in and if you are careful enough, you might see sometimes it does. So that means in tropics, you have to study not only the essential instability that drives and makes convection, you also have to worry about something which kind of without having any anchor like a particular vortex or so, how it sustains on its own. So that's how tropics is different than extratropics. Okay, so I'll skip maybe in the interest of time. Yeah, maybe I'll show this one. Notice what is happening with height, how clouds are evolving. So this guy, notice this guy starts and gets sheared off pretty soon. These are high altitude clouds called cirrus clouds. They start moving out of the slide. These low level clouds also start moving out. So these two, this one very quickly, this one slowly start moving out of the slide. This guy gets sheared off. Yeah, that's what I want you to watch. And this is again few hours of development of clouds. So this means that as opposed to what I showed before, there is a development of vertical development of clouds. Here the clouds are talking to the shear that background flow has, right? So this guy is getting sheared pretty soon, maybe, but not so much here. These are very slowly migrating. These ones are pretty quickly migrating. So there is a vertical gradient of winds that is important. And these are all important ingredients for understanding tropical convection, as you will realize. Yeah. So another situation where you will notice that this guy, which is a kind of cloud system associated with a tropical wave, is predicted to become a cyclone on the west coast. So that's Africa, that's South America. It's predicted to become a cyclone. And the question is, given a particular nature of wave, what feedback will clouds and circulation have for it to become a cyclone, to become a stronger vortex, then to also anchor clouds? Okay, so that's the question we are worrying about. I think I have around 15 minutes and I want to talk about basics of dry convection and moist convection, which I don't want you to miss. So I'll quickly move on to next slide, which now goes to something that we have been discussing before. So that's a classic case of Rayleigh-Bénard convection. I hope everybody has seen this before, where the setup is the bottom plate is heated, the top plate is cooled at a particular rate, and you let system evolve. And the distance between these two is not much. And then you see these well-formed patterns, which in the top view look like that, hexagons. So these are called Rayleigh-Bénard convection rolls. Something I don't know if you have seen, if you have put water for boiling, you see sometimes Rayleigh-Bénard like, but just that note that there is no cooling at the top. Instead, water is getting evaporated. So it's a bit different phenomena. The Rayleigh number, which shows how effective is diffusion versus how effective is convection, mass-related transport. Rayleigh numbers are of the order of 2000. Do you see these? Yeah. 2000 here, it's 10 power 4. But neither of this is a good analogy for atmospheric convection. If you want to make a mental kind of jump from this, there's a nice problem called Prandtl problem, which is where you see atmosphere is an atmosphere with bottom heated, and there is uniform cooling in up to a particular depth. And what happens? What kind of controls the system? And you can show that with a particular scaling that the AD time scale is associated with, which is essentially a similar argument to what Rayleigh-Bénard convection shows. The point being, this is good, but what we want to look at is Rayleigh numbers of 10 power 12. And this is because the scales in the atmosphere are of the order of kilometer, right? The order of kilometers. And because that happens and the buoyancy, as I showed you before, is governed by latent heat release, you have these insane Rayleigh numbers, and 10 power 12 is just the beginning. There are convective storms where it goes all the way until 10 power 15 and so. And that means all our ability, I think Jim very nicely showed all our ability in terms of computation, how much Rayleigh number can we compute, is pretty much limited. We are not able to do this with phase change. So that's the limitation we are running through. The other aspect which is different in atmospheric boundary layer or atmosphere in general in the atmosphere, as opposed to what previous people have told, is that in the atmosphere, density is a function of temperature, pressure, and humidity. So that's atmosphere. Yes. Yeah. So in the shallow water, I think Jim showed it was mainly function of temperature, right? Or height. Temperature or height. That's what it was. In the ocean, I think Mani showed it is function of salinity and temperature, right? So the pressure dependence of density is different. And that means you cannot just look at a temperature of a particular blob of air and predict what will happen to it. Now we are worrying about much more about vertical displacements than horizontal displacement. Mind you that. So if that were to happen, that means if rho were to be dependent on temperature, pressure, and moisture, then how to decide if it is stable or not? Or once you give it enough kick, it will keep on rising up. So to kind of handle that, what alternate method is it's called parcel method. So you have an imaginary blob of air and you give it a little kick. Who gives it a kick? We give it a kick. And you will realize this really matters later on. A little kick, and what happens to it? When it goes up, when we kind of take it adiabatically up, that means we are not doing much, although we are doing a bit. Then does it come back to its initial position? I think Mani or one of them mentioned about this, that if it comes back, you call it Brunt-Weisela frequency, it will keep on doing those waves, right? But in this case, you have to be a bit more careful because the buoyancy will be function of all these three. And that means you have to characterize it one way or the other. So one way of doing it is to kind of find invariant which does not change, invariant to a particular process. And one can show that, I think in the interest of time, I will not derive this, but we can show that potential temperature, which is theta, which in the atmosphere is given by P naught, which is a reference pressure, R by Cp of dry air. So this particular theta is invariant as you basically, if you do this change. And if theta were to not change, then under an adiabatic process, you can actually show this very simply by starting from, can I take 10 minutes more than, yeah, thanks. So by starting from first law of thermodynamics, you can show that first law of thermodynamics can be written, sorry. So this is basically equivalent of enthalpy. This is equivalent to the work done behind the curve. I don't know if you, so this is du plus pdv, right? That's what we are used to. In the atmosphere, since air parcel is expanding, you prefer doing it the other way. You say that enthalpy, which is u plus pv. So this is, so dh is du plus pdv plus vdp, right? And then you can say that du plus pdv is dh minus vdp. And this is a much better framework to look at atmosphere because you could write this nicely thanks to all the experiments others have done. We can nicely write this in terms of these exact functions, right? And then you could say, if you apply heat, then either change in enthalpy will happen or some work will be done on the parcel. This was by the parcel, this is on the parcel. Yeah. And if you then, this is very simple to manipulate then, right? You kind of integrate this. If you say that this is adiabatic system, you could make it 0, define another variable called theta, you can say that this is, and find out what is theta from this. Yeah, you can integrate this from a particular temperature to theta and find out. The point being, this theta is invariant with height, and this gives you a stability measure of stability in the atmosphere. So let's go to what Parcel method gives. So if your theta, which is the background theta, which is shown in red here, if it's vertically uniform, and if your parcel follows that, then at all levels, atmosphere will be neutral. That means parcel taken from A level to B level will want to remain there. If theta background profile, which is set up by other processes, and you are trying to raise up your parcel, if theta parcel was lesser than theta, that means cooler, although remember this is not just temperature, this is a theta, which is a newly constructed temperature, then it will want to come back to its original position because it's just heavy than the environment, and vice versa here. And in this case, it is unstable. Unstable implies that it will want to do the same again, right? It will want to continue from here to above, and above it will be a similar situation, and it will keep on doing it until it finds a level where this is violated, and then it's unstable, and convective instability would have triggered, right? Instability. Okay, now let's try to see the observations. You'll notice that potential temperature, which is shown in the, oops, again, I don't see if you can, but yeah. Potential temperature is almost vertically uniform for 4 different times of day. And this particular instability, if it exists, develops pretty quick. And within no time, you will see that this temperature, potential temperature is homogenized. And then there is a background temperature profile, which is neutral then in the boundary layer. Now let's look at what is its link to what others have been talking about. So let's look at dry convection as buoyancy driven circulation. Let's define it like this. That means there are thermals, fluids which rise up, and then if it's moist, become clouds. And then let's consider vertical motion of these. Look at the potential temperature and dry static energy conservation for these. And let's assume resting horizontally uniform basic state. We have not been doing this horizontally uniform because we are interested in the vertical transport. So if you were to do this, and if W prime were to be the kind of kick that you want to give vertical motion, then the departure from hydrostatic equilibrium, something that Jim mentioned, right? That hydrostatic equilibrium or balance is the background state. And things like convection want to kind of produce departures from such a state. And that's one kind of example of that. Departure from hydrostatic equilibrium. And then this is basically buoyancy force in rho prime g. And S prime is the equivalent of theta, which we call, you can, for all practical purposes, you can think of S as theta. There is a bit of a catch. If there is, we will take a 1 minute diversion. You can notice that this is defined as theta, which is this. If you can make hydrostatic approximation, you can bring in notion of, you can bring in delta Z here, if you can see. If you can differentiate this with Z, then you can replace dou P dou Z, right? Hydrostatic balance will give you, right? So you can differentiate with Z and put minus rho g in the mix. And rho is governed by equation of state. So then you can basically find out, you can kind of construct another quantity which is like theta for all practical purposes, just that theta is true even if it is non-hydrostatic. You can construct another quantity called S, which is dry static energy, which is this, I think in Jim's talk was phi or phi. This is called geopotential. So how much internal energy you have, how high you are in the atmosphere. These two give you this dry static energy. Where is the, oh, here. Dry static energy. And then there is, so if you were to write down dry static energy, and if you were to assume that there is this particular background profile of dry static energy or theta that's given, then you could solve this simple system. Again, use the same mechanism that others have been using, right? Substitute a type of solution. No? Oh, yes. Substitute a type of, so another thing you want to assume is, again, I think some others have shown that you can show that density perturbation with respect to, I think this is not working, so I'll just stop using it. Density perturbation with respect to background density scale as changes in, so this, can you check this? Yeah, temperature perturbations. And you could solve this system. So slide change works. Yeah, this one. Yeah. Okay. You could solve this system assuming that there are solutions of wave type where sigma can be either real or imaginary, and you could get such a expression for sigma. You'll notice that this depends. This is a bit like what others showed, right? Dou B, dou Z, where B was buoyancy before, was n squared, right? This is a bit like that, but in the dry atmosphere. And in this case, you can show that it is a function of T bar and the stability parameter in the background. So what we described before, just notionally that the parcel will want to come down or something else, now we are able to nicely show that if dou S bar by dou Z, which is the theta profile or dry static energy profile, if it is less than 0, then sigma is real. And sigma is real is the, sigma real would imply that it blows up, right? E power sigma T. So that means W prime will want to get blown up, also S prime. And you could show that this is the stability criteria. Another very simple thing which I don't have time to show, but another very nice thing you can show in this particular case is that if dou S bar by dou Z is positive, then sigma is imaginary. So which I have not written. Dou S bar by dou Z greater than 0, sigma is imaginary, is complex number. And if this is a complex number, then that means these are wave solutions. So all the gravity waves would sit here. One very nice thing comes out of this analysis is that convection, which was the instability part, and wave solutions, they are independent of each other. So in dry convection, you can either have gravity waves or you can have convection, which is unstable, right? Parcel goes up, up, up until it kind of violates that particular criteria. The whole point of me showing this again is to show, first of all, one nice property of dry convection, but to also show that what happens when you add moisture in the mix. When you add moisture, let's consider these observations. So there is this particular profile of specific humidity. Oops, yeah, this one, which is observed specific humidity, corresponding saturated specific humidity by Clausius-Clapeyron, dependent on temperature, is this. And that means if I were to raise my parcel, started from here and raise it up here, this is the corresponding level at which it will want to make clouds. That's where it will satisfy the condensation criteria. And if that were to happen, it will maybe make a particular, it will follow a particular profile of something which we call moist adiabat. And that means in terms of temperature, initially, when you raise it up, it will be cooler, cooler, cooler. At some point, when it starts undergoing condensation, it will follow moist adiabat. And it will have a particular amount of energy because it is warmer than environment for it to drive circulations around it. So that's the kind of amount of energy it has to drive pressure gradients, generate flow, maybe generate turbulence of different sorts. Yeah, so that's the amount of energy. The catch here is that this is not ensured. So at some point, if you have enough water vapor that condenses at a particular level, then you will have water vapor like clouds and so on. But there could be some parcels which have lesser amount of water vapor lying at the same altitude. They may not undergo such an instability. In that particular case, you basically cannot predict, you cannot use what we did before. If this was a definite process of clouds undergoing condensation, you could have used another. So you could have said, oh yeah, this air undergoes condensation here. So use saturated kind of values to predict when will cloud form. This being conditional makes life a lot complex. So that means you realize you cannot do the stability analysis and couple it to the dynamics as we would have liked to do. So then temperature profile looks like a dry adiabat. In case of moist adiabat, it's a bit warmer. And if temperature falls at a higher rate than dry adiabat, then it's definitely absolutely unstable, right? At all levels, it is going to be kind of warmer than its environment. This is absolutely stable. It's always going to be cold. In this murkier area in between, it's conditionally unstable. And this is very different from all that we have been hearing. Just to highlight, don't get bogged down by several colors here, is the same trajectory of parcel that it undergoes. To highlight that, the red is the amount of energy parcel will have if it were to cross and undergo condensation and so on. But this is the amount of kick in terms of energy that it requires. What provides that kick? We have been assuming we provide that kick, right? That's the mechanical kick we provide. What provides that kick? One of the answers could be the nice structures in, let's say, force by convergence, divergence pairs, vorticity, and so on, right? Orography. They all will provide that kick so that it crosses the barrier and goes up. So the kind of key point being that there are these two reasons why we cannot use QG-like linear theory to analyze this. What we would have really liked is to do a linear perturbation analysis, right? You assume an infinitesimal perturbation. I think somebody talked about it before. You apply infinitesimal perturbation and see if it grows or not. In this case, for two reasons. One, your atmosphere is unstable to a finite amplitude perturbation. And we don't have a nice math kind of theory developed to analyze how atmosphere responds to finite amplitude perturbation, analytical theory. The other thing is that the condensation criteria depends both on temperature and humidity. Unlike before, you cannot just do kind of a simple take temperature equation, club it to say Navier-Stokes and do a perturbation analysis. You need to include both temperature and humidity, and then you can analyze how clouds will evolve and so on different time scales. So that's why it becomes, so our only nice tool, analytical tool of linear stability is now not available. Then what all goes on actually in the reality is things develop. So for a particular very simple type of cloud which develops as layers, which is called stratocumulus cloud, usually observed away from the equator in mid latitudes. There is radiative cooling. That means this cloud is cooling from top, unlike Rayleigh-Bénard, right? We have been seeing it's heated from below. So the turbulence is driven because it is cooling somewhere in between. So it's cooling from top, that is driving turbulence below it. And then that turbulence will probably enter in kind of dry air from top, from below, or from other kind of regions. It might even break this. So a typical length scale of this could depend on how quickly can such a cloud structure be broken by a particular wave pattern, for example. Okay, so but in the tropics, we see this not happening quite often, as I showed you before. We saw that it's more like popcorn convection, whereas in mid latitudes, the clouds like to ride on the waves. So one very nice thing to kind of think about is to think of the thermodynamic diagram, that it has amount of energy, there is a kick, And then to think of a cloud development on the right-hand side, where the cloud is entraining at all different altitudes. It is generating its own vorticity on cloud scale. The kick could come from larger scale, as we were talking, right? From a larger scale convergence, divergence, or a vorticity, particular vorticity pattern. And then that could be one conceptual model of the clouds. Okay, so until now I have been telling you that why we are not simply starting with Navier-Stokes equation, use Reynolds transport theorem and club temperature and humidity to Navier-Stokes and just solve the system. And solve the system analytically, as some of the previous speakers were doing, and all the nice machinery we have. The trick is this notion of stability is complex and depends on how energy profile looks in the vertical. In the interest of time, I'll maybe skip this slide, but show you that in observations, the equivalent of this is the dry static energy. If we were to consider moisture in the mix, we can do, and so far as the processes are reversible, processes are nice, there is no condensation that falls out, there's a nice thermodynamics one could do. One could show that this plus where Q is specific humidity, that's the amount of energy it has, irrespective of what happens to it, this particular quantity, then it's called moist static energy. So one could kind of try to frame the same problem, but in terms of moist static energy. And then, as I told you, it's conditional instability that controls everything. If one were to make an approximation on push it to the other limit and say that if the whole of atmosphere was saturated, one could try to do a similar thing and try to derive a particular growth rate or particular whatever, depending upon if it's real or imaginary, as a function of saturated moist static energy profile. This gives one limit of what might happen. Dry is the other limit of what definitely does not happen at many other places. And reality lies somewhere in between. So we know bounds, but we don't know exactly what happens in between. Okay, so the total energy, this is the third last slide. Yeah, I have already taken 10 minutes more. So the total energy in the atmosphere, which is made up of moist static energy, which is made up of internal energy, potential energy, which is work done against the gravity, right? And then latent energy, which is available in terms of water molecules. And there is kinetic energy. And you will realize that kinetic energy is actually 0.05% of the whole mixture in the, but kinetic energy implies flows, right? So flows carry water vapor, flows carry temperature, flows either push things up or down. So in some sense, don't go by just these numbers that internal energy is 70%, this is 30%, this is like 2%. Ultimately, the coupling of these two, because flows will carry internal energy, potential energy at different levels, you will have to, this kind of contribution will keep on changing as things happen. I'll skip this slide, but just to show you that when we ultimately want to solve things, we then rely not on just simple analysis, but we very soon will have to rely on coupling, momentum, thermodynamics, water vapor continuity, mass continuity, although it's written like this, mind you that rho is dependent on pressure, so one will have to kind of account for incompressible effects, although this I've kind of taken liberty not to mention it here. But you will have to worry about incompressibility. And then if convection is occurring, then departures from hydrostaticity. And then you will have a kind of full system of equations that you can solve along with equation of state to get some idea of what is going on. And whatever is on the right-hand side is nicely written as physics here. And that's where the real challenge really appears. So physics is controlled by in the equations of motion. Others have said about turbulent transport, generation or dissipation mechanisms. For thermodynamic energy, all the radiative, convective processes, that kind of summarizes all that goes on that we described. And how sources and sinks for water vapor in terms of evaporation and so on. So then it will be a complete kind of set of equations that we will want to solve, assuming things are reversible. So this is what we would like to actually solve at all different scales. Couple all of them, do a simulation at all different scales, and look at what you get out of it. But as Jim showed before, that even the problem with turbulence or shallow water equations, you are not able to solve those equations at, this is a bit kind of one complexity added on top. So you cannot solve at all different length scales and time scales. So what you end up doing is you choose an area and say that everything else is subgrid scale. And sometimes what you do is all that complexity that's here in a particular area, that means a cloud is developing, there's a downdraft, it is entraining from all the different sides, it is kind of enlarging from the top, there's other cloud which is wanting to grow, maybe this is trying to kill it. All this is subgrid scale variability. And the real challenge is to explain, kind of write this as one kind of some representation in the large scale module. So either you say that I will resolve this, so I'll kind of choose a model which simulates this, resolves all the fluid dynamical scales, and will learn out of this and put it in the large scale model, or write some representation of this and put it along with the large scale model. So this is the this is the left part of this is a large scale model. The right hand side is all the either the parameterization or what very high resolution fluid dynamical simulation should inform to the larger scales. And then we can say, oh, we had some representation of moist convection in the mix. So the take home messages are very simple. Out of so many things I said, there are 3 unique properties of water, and you should remember them. They really modify how Earth's climate is they really shape Earth's climate. Clouds and circulation interact on variety of time scales. I showed you sometimes they just develop like popcorn. Sometimes they are anchored through vorticity on different length scales, time scales. Dry convection and moist convection are very different. And the trick is because it's conditionally unstable. You cannot use your simple linear stability, finite amplitude perturbations. And then it is a challenge, is a numerical kind of challenge to resolve all different scales, and a hierarchy of model is quite used usually. Sorry that I took more time, Jim. Yeah,
let's have a couple of quick questions and then we'll break for coffee. Yes, there.
So in ocean, we have 2 scalars, temperature and salinity. Similarly, in atmosphere, we have humidity and potential temperature, right? So what is the scale separation between these 2 scalars? Because in the ocean, the ratio of diffusivity of temperature to salinity is about 100. I was wondering if there is some scale separation here as well.
There is no scale separation. Actually, ocean, for example, is advection diffusion problem. Advection diffusion problem. Atmosphere is much more radiation convection problem. And radiation is photon scale, electromagnetic radiation. And convection is all scales which are depending upon forcing, right? So there is no such scale separation in the mix.
But when we would write, let's say, scalar transport equation for both humidity as well as for potential temperature, let's say. So the diffusive term will have molecular diffusivities.
Yes.
So are they of similar order of magnitude?
How big are molecular diffusivities is the question.
Compared to, I mean, if
we compare both of them. The eddy diffusivities, turbulence driven diffusivities are, say, order of magnitude more, a couple of order of magnitude more than molecular kind of property related diffusivity.
But if we compare just the molecular between the 2 scalars, humidity and temperature.
Yeah, I don't know. I don't know. Maybe Jim, do you know? Temperature and humidity, yeah, I don't know actually.
Because in the ocean we have double diffusive convection because of the difference in 2 diffusivity. That was one.
No, double diffusive convection does not happen here. There it's the opposing gradients, right?
Yes, opposing.
In terms of density, that does not happen here. Okay. Unless there are few. There's a very nice paper which was recently written called I forget the name, but I could say this. So what they show is because molecular weight of water vapor is lighter than dry air, it can happen that just because of molecular weight, water vapor is wanting to escape, but it's cold. So because it's cold, it's the mixture of lightness of water vapor, and so, but that's not the dominant phenomenon.
Okay.
Yeah. only few times you see this. Maybe in a first few tens of meters, you sometimes see this. In general, it's not all pervasive phenomenon.
Any other questions?
In one of your animation, I thought it was status at the downwards. So, okay, in one of the animation that you saw, turbulence was happening more with height. Is that the proper conclusion I can draw with that? I mean, it was a status downwards, and I thought it was a cumulus clouds upwards, or at least they were having more of turbulence, or they were rising up.
Sure.
Yeah, here it's a height phenomena. You see, like, can you on the animation again? This one, yes.
Yeah.
Yeah. So it's okay. I mean, the downwards doesn't seem to have turbulence, but the upwards seems to have turbulence.
Oh, you mean near surface?
Yeah.
It's not visualized, right? Water vapor is still not condensed. So all dry air molecules are invisible. If you had some nice tracer on top, you might see those thermals, which are causing these clouds to grow up.
Okay.
Yeah.
So it's not a height phenomena, right? Like.
So if you're saying that if the turbulence is absent here, that's definitely not the case. It's not seen here.
Okay.
Yeah.
One more question. Last question. As fast as there.
In these parcel type arguments, how do you include diffusion?
Diffusion. So these parcel type arguments make several assumptions. First of all, the parcel goes up and immediately adjusts its pressure to its surrounding. And even if there is a diffusion that is active because of the gradient and so on, that's a kind of small scale phenomena which on the time scales of parcel development will not matter much. They have not been kind of, at least we know from some DNA simulations, it's fine too. Although the parcel theory itself has several limitations, but that's where we are right now.
Okay, so we'll end there. Thanks a lot, Vishal, for the nice talk. We'll thank you once more.